Thank you folks for joining. Rashid here and another video on the microarchitecture series. And today we will look into our second instruction, microarchitecture of the second instruction, and that is load word over here. Okay, the first one was add I. So we have we look into the block diagram of that. This is pretty much add I. And then we look into Python code that I'm using for modeling add I. And yeah, so far we did 2-3 videos on Python, so hopefully you understood the concept. Anyway, if you this is first time you are watching this series is for members, and the membership is very reasonable, $2.99 if you are in US or Europe, and if you're in India, it's I think 89 rupees per month. Okay, so let's get started. In this video, I will show you the block diagram of to implement this instruction, as well as I will show you Python code. I made some changes to the Python code, the basic structure of it. So I'll show you that in a minute. But plan is not to spend too much time on Python code because I've already explained the major components of it. So I'll show you quickly some of the updates, and we will run it, and we will see both instructions, add I and load word being executed on Python. Okay. All right, so let's get started. Load word, it is also an I type instruction. If you remember, different RISCV type and JU type. Those are the 4 So load word is here, the add I was here. So load word, the op code, it will be 3 in decimal, and those func 3 bits will be the decimal 2. This is our 32-bit instruction. And in I-type instructions, what we have is first 7 bits are for opcode, then 7 to 11 for the destination register, 12 to 14, these are the number of bits for func3, and 15 to 19 are source register. There's only one source register. And this is the immediate. Sign and could be sign on X sign, but we expect it to be signed. Okay, so this is good that every time we review it, hopefully you will, by the time we go through it, you will remember it on your fingertips. Okay, so the syntax in assembly is something like this. Now I have written it in terms of X sum register as opposed to A0, A1, A2, or S0, S2, 3. Okay, you understand that. And load word, what happens is this is the source register, and this is the destination register. So load or store, always they operate on the memory. So what happens is we need to bring data, loading the register. So we will load this register with a word that is located at this location in the data memory, not in instructions. This itself is an instruction, right? There's an entire hexadecimal value, 0101 value, binary value of this 32-bit stored in the instruction memory over here, right? But this time, first we bring this instruction from the instruction memory. So let's say at PC some address, which is a 0 address, is available right now here. When that, we have this instruction available in the memory somewhere here. And then we put that address connected to this 0 immediately, after some delay, of course, because all these signals travel with certain delay. But here we are not assuming any delay. So whenever we have address, the data is available. So 32 bits come here. And now from these 32 bits that we have, we pick where we need X3, the value in X3 could be any register, right? Any of those general purpose registers, except X0, of course. So X3 can be X0 too, but it is not. We don't change that. So X3 and the 8 value. So this is 8, and this is X3. These 5 bits represent the X3. So 0, 1, 2. Then the value on X3. We read that from register file and we add that to 8. So And then that becomes the address of the data memory, from where we read the data and load it into X10. Understand that? Excuse me. So the data that we need to move to X10. Sorry, 1 second. That data is not in the instruction memory. So instruction memory has this instruction. It tells us which register source, which destination, what is this value, and the load word, right? So then we need to go read X3, which is source, add it to 8, and then read the data memory. And from there we bring the value and put that into X10. So this was our add-I. By the way, I'm assuming that these 3 bits are, what was the load word? 2. Okay, so this instruction comes, this time this 32-bit, right? This is the same way 19 to 15, because it's also arch type, so this structure remains the same. 19 to 15 is our what? 19 for source register, right? So this is the address of the register. So as soon as this value comes here, the read 1 comes at the output. So we get this value, correct? And then the immediate here, 31 to 20, which is 12-bit, since we are adding the two together, because the address is this one, we add 8 to X, the value of X3, and we will use ALU, and we need to send a signal telling ALU that it's addition of these two. And the output of ALU, last time we wrote it back to the register file, and the address where we want to write is this, but this time is a little different. This address stays the same, there is no change in this connection, but this time we need to write not the output of ALU, but actually we need to bring this data memory here. We connect the address there. So this address, this output goes here, that is the address from where we will read data. Okay, so instead of, I will do it live here. Let's break this, because previously, remember, we wanted to write output of ALU. So now we can't connect two there. There's only one write data, 32-bit, right? But we need to decide whether we write between ALU or we write, let's, wait a second, we bring the output of, right? Then we bring it all the way here. It's not straight. Okay, right? So then we need to, okay, let's keep it. All right. So now what we need to do is we need a device here, and you know which one it is. So what needs to happen is when it's add I instruction, then this connects to this, and when it's this current load one instruction, then output of this one is connected to this one. And you know which device is that, right? That is a multiplexer. So I already created that multiplexer. Okay, it fits that nicely. And let's move it out and bring it there. All right. So all we have to do here now, we have to control the multiplexer control pin. Let's call it data mem to register file. When it is 1, we say we pick this. When it is 0, we pick the ALU. So just like this control where we had this and this here, now we also need a control. We need to have a signal. I don't know if I should draw these controls or not. So maybe I should do is wherever, Okay, hold on. Wherever we have these, this highlight, it's a control one. Okay, because otherwise this picture will become very difficult to understand if we draw lines all over the place. This is control and this is control. Okay, that's good. Makes sense, right? So that's it. Now this block diagram represents is going to implement both add I and load word. And of course, this control logic that we bring from here, that is super critical in enabling that. That when it's add I, this decode that happens inside control, that ensures that right signals go for add I and the other case right signals for the load word. Makes sense? I think that's it. Simple enough. And again, always good to look into the context of when I say PC value is this, that means previously a clock edge happened, and when we started this, there was already a value at the output of PC. This goes to we bring from the instruction memory, right? We bring and we decode it. This is kind of control as well, right? We decode it, and then we send signal. We send those wiring to the register files, right? We also do sign extension. We'll bring them, add them together, read the data memory. Then we have that multiplexer into register file. Our timing path actually starts on PC, ends on this register file. And this all happens in one clock cycle. So how much is the delay from here to here? That is the delay that we need to have a cycle. And the cycle delay is inversely, and you inverse it and it becomes the frequency, right? Makes sense? So this is what happens is right after some time, there's some delay here which I'm modeling here. I mean, right now we are not assuming any delay. So after that, what happens is our control signals are available. This time we have a write to reg. Of course, we need this control we need, right? And this we need. Eventually, you will see that this ALU not just adds it can subtract things, it can AND things, it can OR things, it can exclusive OR things, right? It can do those operations, and it can do maybe compare as well. We'll see. So we need to put right signal to the ALU, and typically that will be more than 1 bit. That's why I'm drawing with something like this as a bus. Understand that? Hopefully it's clear. I think I'm going to do the Python code for this in the next video because otherwise it will be too much. If you got any question on this, please let me know, and I will see you in next video with the Python code for both of these instructions. All right, see you, bye.